Hello, in this video I am going to solve another problem from the famous STEP exam. The question that I have chosen for this video is question 1 on paper 3 related to exam 2021. So let us read the question together first. A curve has parametric equations x equals to minus 4 times cosine t cubed and y equals to 12 sine t minus 4 times sine t cubed. Find the equation of the normal to this curve at this point, where phi is a fixed angle between 0 and pi over 2, fixed number between 0 and pi over 2. After that, we are supposed to verify that this normal is tangent to this curve at this point, where phi, of course, you see is the same phi introduced here. Okay? Before actually start reading the second part, let us just solve the first part, and we will come back and read the second part and then continue the solution. Okay? Okay. So here, the parametric form of the curve is given in this form, and then we want to find the normal to this curve at the point A with these coordinates, where phi is a fixed number between 0 and pi over 2. Okay? So first of all, I want to draw your attention to this point, that immediately you realize that this point is on this curve, because if you replace the given parameter t with that given fixed number, then the x coordinate becomes exactly this, and the y becomes exactly this. So definitely this is a point on this curve for the value of the parameter t, which is equal to phi. And you know that if you want to find an equation for the normal line, you need to find the slope of the normal line. In order to be able to find the slope of the normal line, we use the notion of derivative to find the slope of the tangent line, and then using that, by taking the negative of the reciprocal, I will get the slope of the normal line. But of course, because this equation, this function is actually given in a parametric form, the derivative that I will take is also in parametric form. So you know that if, let me put this in a box. So if x is a function of t, and y is also a function of t, let us say g of t. So in principle, y is also a function of x. And if I want to calculate the derivative of y with respect to x, what can I do? I can take the derivative of y with respect to, I can take the derivative of, so let me write it like this. If I want to take the derivative of y with respect to t, I can write the derivative of y with respect to x multiplied by the derivative of x with respect to t. That is just the famous chain rule. But in this case, I want to calculate dy dx. So if dx dt is not vanishing, is not zero, then dy dx is equal to dy dt over dx dt. So I'm just refreshing your memory about parametric differentiation, yes? So dy dx is equal to dy dt divided by dx dt, if this expression is not zero, of course. Of course, and now here you see y is g of t, so another way of writing dy dt is to write g prime t over dx dt. Another way to write it is just f prime t. So this means that this will be, so this is the derivative of the function y with respect to x, which is necessary for this problem. But we have a better way to do it. We take the derivative of function g, and then I divide it by the derivative of function f. Okay? So if you don't mind, let me just clean it. We don't need it anymore. But what we learn is to take for finding the derivative of y with respect to x, I take the derivative of this function with respect to t, and I take the derivative of this function with respect to t again, and I divide the former by the latter. Yes, provided that the denominator, of course, does not vanish. Okay. So dy dx, is equal to the derivative of this function with respect to t, which becomes 12 cosine t. The derivative of this one, 3 goes down. It becomes minus 12 sine to the power of 2t, but I have to multiply by the derivative of the base, which gives me cosine t. And then I divide it by the derivative of x with respect to t, so this becomes minus 12 cosine to the power of 2t multiplied by the derivative of cosine, which is minus sine, so this becomes positive sine t. Now let us do some simplifications. So immediately you realize that I can factor a 12 cosine t out, and then I have 1 here and minus sine squared here. Minus sine t squared, and then I just copy and paste this part, so it is 12 cosine to the power of 2t sine t. Okay, so I do some simplifications immediately. So this 12 here and that 12 are cancelled. 1 cosine will cancel 1 cosine. On the other hand, 1 minus sine t squared is nothing except cosine t squared. So 1 cosine and 1 cosine are simplified. 1 cosine in the denominator is left and 1 sine is also left there. But 1 cosine will be cancelled here. A cosine will be left in the numerator. A sine will be left in the denominator, which is cotangent, yes? So we found that the derivative of y with respect to x is cotangent of t. Okay, but if I ask you what is the slope of the tangent line at that particular point which corresponds to this value for my parameter, so I would say the slope of the tangent line, so let me show it with t, slope of the tangent line is equal to the derivative of my function calculated at the point that I am interested in, which corresponds to value phi for the parameter t. So then it becomes cotangent of phi. So this is the slope of the tangent line. But I am interested in the slope of the normal line. Okay, so then the slope of the normal line, so let me use this notation for that, it's m sub n. This becomes the negative of the reciprocal of cotangent, which of course is minus tangent. Is it acceptable? Yes, because you see that phi is a number strictly between 0 and pi over 2, so there is no danger of that undefinedness or something like that. Okay, so this is the slope of the normal line, but I want to write its equation. So what I do, I use this idea, I use this formula, which is, we know it very good. So here y node is the y coordinate of the point of tangent C, or the point that you have the normal line at. And then x node is the x coordinate. So I put these things here and try to simplify them if possible, okay? So what happens, this becomes y minus, y node is this expression, I multiplied by negative sign. So the first one becomes negative, the second one becomes positive. Sorry, this is not 12, this is 4. On the right-hand side, instead of the slope, I put minus tangent phi, and x minus x node. But x node is this expression, so minus minus becomes positive. Okay, so that is the equation for the normal line. Of course, you cannot resist to simplify that, me neither. So let me just simplify it to see if we can write something better. So this becomes y minus 12 sine phi, and then I have plus 4 sine phi cubed, and then I multiply it in, so this becomes minus x tangent phi, and tangent is sine over cosine. One cosine will simplify one of these cosines, so one sine, 4, and cosine squared are left, so this, and a negative sign, so it becomes negative 4 sine phi cosine phi squared. Okay. So what we can do, if you want to write everything in terms of sine and cosine, I would recommend you to multiply everything by a factor of cosine. That cosine that I will multiply will turn this into a sine. Then everything will be written in terms of sine and cosine. So then it becomes y cosine phi minus 12 sine phi cosine phi plus 4 sine cubed cosine phi. On the right hand side I will have minus x sine phi, and then this becomes minus 4 sine phi cosine phi cubed. Okay, and then what I do, I move the x1 to the left to write them in a standard form. So I would write x, if you want I can write sine phi here, and then I will have this one which is cosine phi y, and then I moved everything here to the other side. Okay, so I move this to the other side, so it becomes 12 sine phi cosine phi, and I move this to the other side, minus sine phi cubed cosine phi, and then I have minus 4 sine phi cosine phi cubed. One more step, so sine phi x plus cosine phi y. I take 4 sine phi cosine phi out. Then here I am left with 3. Here I am left with sine squared phi. Here I am left with minus cosine phi squared, yes? So I factored 4 sine cosine phi out. So this becomes 3, and then this becomes minus sine squared phi, minus cosine squared phi. But if I factor also a minus sign from here, then this becomes positive. But sine squared plus phi squared is 1. So this becomes 2, and I multiply it becomes 8. So then it becomes sine phi x plus cosine phi y is equal to 8 sine phi cosine y, which can be written as 4 sine 2 phi. Yes? So that is an equation for the normal line to this curve at this point. Yes? Okay? Okay. Now let us go to the second part of the first part of the problem. Yes? So here, so we found this part, we found the normal actually to the curve at that point, but now we want to show that the normal that we found is tangent to this curve at this point. Okay, now let us see it here. So here, this is the curve given. I want to show that this line, which is normal to that previous curve, it is tangent to this curve at this particular point. Of course, this phi is the same phi we started with. Okay, first of all, I hope that you agree that this point really lies on this curve again, because it matters. If the point does not lie on the curve, so it means that I have to find a way to find an equation for the tangent line from a point outside the curve. So this is why I actually test this idea, why this lies on this curve? Because it is simple to see that the coordinates satisfy this equation. Why is that? Because if I take this one to power 2/3, so 8 to power 2/3 is 4, cosine phi to power 3 to power 2/3. So let me just check it. So the left-hand side is equal to, instead of x, I plug that in, plus, instead of y, I plug that in. But the answer to this is just 4 cosine squared, plus the answer to this is 4 sine squared. And then if I factor 4 out, the answer becomes 4, which is exactly equal to the right-hand side. So it is simple to see that this point B actually lies on this curve. Okay, now we want to find an equation for the tangent of this tangent to this curve at that point, and see that this is exactly that line, that we have that equation there. Okay, so how should I do that? This is an implicit function, so I have to do the implicit differentiation. So I take the derivative with respect to x. So the derivative of the first term with respect to x is just 2/3, x to the power of minus 1/3. And then this becomes 2/3 y to the power of minus 1/3, but you have to multiply by y prime. On the right-hand side, the derivative with respect to x is, of course, 0. And from this, I'm supposed to find y prime. So I move the other this term to the other side. These 2/3 are cancelled, actually. And then y prime becomes negative. You divide this by that, but because this is minus, that's minus, I flip that. So it becomes, let me write it down. So it becomes x to the power of minus 1/3 divided by y to the power of minus 1/3. So this becomes minus y to the power of 1/3, and then we have x to the power of 1/3. And then I can write it as minus the third root of y over x. Okay, so this is the derivative of this function. But I want to find the tangent, the equation for the tangent line. So this is the point, this is the derivative, so I calculate the m of the tangent line. So let me write m of tangent line, but for this one, not the previous one. Okay, so what should I do? I need to replace these two here, so this becomes minus the third root of, instead of y, I put this expression, and instead of x, I put that. And then what happens? So this 8 and 8 are cancelled, so this becomes tangent cubed, but this is the third root, so it becomes minus tangent of 5. So this is the slope for this, for the tangent line to this curve at that point. But let me write now the equation. What is the equation? Again, the equation will be y minus y node is equal to m tangent x minus x node. Okay, so then this implies that y minus y node, which is this expression, is equal to m of tangent, which is this one, multiplied by x minus x node, and x node is this expression. Okay, and then I have to simplify a little bit. So again, I multiply everything by cosine alpha, because I want to get rid of tangent alpha, because my goal is to compare this equation finally with the answer that I got. I want to confirm that this equation can be simplified or rewritten in that form. That's the point. Okay, so I multiply everything by cosine, so then it becomes cosine phi multiplied by y. If I multiply this by cosine, it becomes minus 8 cosine phi sine phi cubed. And on the right-hand side, the cosine that I am multiplying will be simplified by that. I will get minus sine phi, and then x minus 8 cosine phi cubed. And let us simplify it a little bit more. So let us just do some part of it in our head. So I multiply minus sine phi here, it becomes minus sine phi x. I move it to the other side, it becomes positive. So this becomes sine phi x. I have already this here. Okay, and then I want to move this term to the other side so it becomes positive. And then I am left with this term here as well. So minus sine phi times minus 8 cosine phi cubed, it becomes positive 8 sine phi cosine phi cubed. Again, one more step probably, yes? Between these two, I can factor 8 sine phi cosine phi. From this, sine squared is left, from that cosine squared is left, but of course sine phi squared plus cosine phi squared is 1, so that's the answer. And then you can just write this back again in the form of 4 sine 2 phi if you want to. And then if you compare this equation, which was the normal line to the previous curve, coincides exactly with this equation, which is the tangent line to this new curve. Okay, so this will actually finish the first part of the problem. Okay, now let us go and read the second part and do that part as well. Okay, part 2. A curve has parametric equations x equals to cosine t plus t times sine t and y equals to sine t minus t times cosine t. Find the equation of the normal to this curve at this point, where again phi is between 0 and pi over 2. And then determine the perpendicular distance from the origin to this normal line, and hence find the equation of a curve independent of phi to which this normal line is tangent. Okay. Okay, so now we have this curve, the parametric form of another curve. We want to find the normal line to this curve at this given point for a particular value phi, which is fixed in the interval between 0 and 1 over 2 pi. Again, comparing this with that one, you see that's exactly the same expression. The only difference is that t has been replaced by phi, the same thing here. So this means that this point also lies on this curve, because the coordinates of this point are achieved when you replace the parameter with phi. Yeah, so that's a point on this curve as well. So the problem is as before. I want to find the normal line. Again, I find the derivative in a parametric form. So the derivative y prime is here, the derivative of y with respect to t divided by the derivative of x with respect to t, yes? So the derivative of y with respect to t is cosine t. Here I apply the product rule, so this becomes the derivative of the first one multiplied by cosine, minus this multiplied by the derivative of that one, which becomes positive t sine t. Yes? Divided by the derivative with respect to t here, so this becomes minus sine t. Product rule is applicable here, so it's plus sine t, plus t times the derivative of sine, which is cosine. And then this one and that one are simplified, this one and that one also simplified. I am left with t sine divided by t cosine. T's are cancelled again, so then it becomes sine over cosine, which is tangent. So this y prime is actually tangent of t. But now I want to find the slope of the normal line. First, I find the slope of the tangent line. So slope of the tangent line for this particular case is the same thing, but I have to replace t with the corresponding value for my parameter, which is phi. So this becomes tangent of phi. Then it means that the slope of the normal line is the negative of the reciprocal, which in this case becomes minus cotangent phi. Yes? Okay, and then I would write the normal equation, the equation for the normal. So this becomes y minus y naught. This will play the role of the y naught here. So I put here, it becomes minus sine phi, but plus phi cosine phi is equal to the slope here, which is minus cotangent of phi, multiplied by x minus x naught. This is by x naught, so it becomes minus cosine phi minus phi sine phi. So that's it, actually. This is my equation. If you want, you can just express it exactly as before in terms of sine and cosine, but this time I multiply everything by sine phi to get rid of cotangent. So if I multiply everything by sine, so this becomes sine phi y, this becomes minus sine squared phi, this becomes plus phi sine phi cosine phi. Yes. And then here this becomes simply minus cosine phi. And then this becomes x minus cosine phi minus phi sine phi. The rest of it is just simplification, okay? So let us do some part in our head. So if I multiply this here, it becomes minus cosine phi x. I move it to the other side, it becomes positive. So this becomes cosine phi x. And then I have here sine phi y. Okay? And then I move the rest to the other side. So I have minus sine phi squared. I move it to the other side, it becomes this. I have this term, move it to the other side, this. And do you remember? I multiplied this here already, but I also have to multiply it here, which becomes plus cosine phi squared. I have to also multiply it here, so it becomes phi sine phi cosine phi. Okay? And then see, this term and that term are cancelled, and sine phi squared plus cosine phi squared is exactly 1. So what I get is this. Is equal to 1. If you want to, I can move it to the other side. Minus 1 equals to 0. Okay, so that is actually an equation for the normal line for this new parametric curve. Now, we want to find the distance from the origin to this line. Okay, so let me just refresh your memory. So if you have in the coordinate system, if this line has this equation ax plus by plus c equals to 0, and let us say that this point A has coordinates x node and y node, if you want to find the shortest distance, this perpendicular line, if you don't mind, let me call it d for distance, then you have this formula. The absolute value, you replace x with the x coordinate of your point, you replace y with the y coordinate, so this becomes ax node plus by node plus c, and then divided by square root of this coefficient is squared plus this coefficient is squared. So this is the formula for finding the distance of a point from a line on the plane, yes? Okay, so now I have the origin, the coordinates are 0 and 0, so the distance that I am interested in is absolute value. I replace x with the x coordinate of my point, becomes 0. Replace y with 0 is 0. Minus 1 is left. I have absolute value. And then a square root of this coefficient squared plus this coefficient squared. But this is just 1, the numerator is also 1, so the distance is 1, independent of my choice of phi. So that's important. So you see, the distance could in principle depend on the value that you choose, because by choosing the value you choose for phi, because if you change phi, what is happening, the slope is probably different, okay? So if the slope is different, the perpendicular line is also different, and the distance from this point to that line might change. But the calculation shows that no, for this case it is not the case. Any choice of phi will give rise to the same distance from the origin. Okay, now let us go back to the slides again. So determine the perpendicular distance from the origin to this normal line. We already did that the answer is 1 independent of phi, yes? And then we want to find the equation of a curve to which this normal line is tangent. Okay, so so now so let me just give you an idea what is going on. For example, let us imagine that this is the coordinate system and this is your line. For example, assume that this is your line, and the distance from this origin to this line, perpendicular line, d is equal to 1, independent of your phi. First of all, for just this particular setup, you realize that if I draw a circle centered at the origin with radius equals to 1, that circle definitely becomes tangent to this particular line. But the calculation shows that if I change the phi, even though the slope will be changed, so I will face another line, that the distance from the origin to that new line is still 1. Okay, so this is actually very simple now. So hopefully you realize that yes, this circle centered at the origin with radius 1 is actually tangent to all these possible lines independent of my choice of phi, at least in this range that we are interested in. Okay, so I would say that, okay, the equation demanded for that curve is just simply an equation for the circle centered at the origin with radius 1, which is of course very famous to be this. Okay? Okay, so I hope that you find something useful in this video. Until the next video, be safe and goodbye. Thank you.